Welcome back, everyone, to the eCoreAcademy e-learning platform. Today, my name is AJay Raj, back with yet another geometry video for you all. And today's lesson topic is all about prime optimization, something that I've been really excited to show you guys. Another higher level math concept, especially covered in calculus and AP calculus, and also multivariable calculus. But before we jump into today's lesson, please make sure you smash the subscribe button, hit that like button on this video, turn on post notifications, and drop a comment down below. So why exactly am I showing you guys what prime optimization is? This is a topic that is also found in geometry very often in higher level courses for geometry, and of course referred to in calculus as concepts of geometry are heightened there as well. So prime optimization has to do with your area and your volume and how you're going to maximize those potentials. So we're going to look at today what exactly prime optimization is and how it can be applied to real life scenarios and other different problems in which it is applied and utilized. So without further ado, let's jump right into it. So let's introduce this topic. What exactly is prime optimization? What's the definition? I'll give it to you right here. So prime optimization is a process of developing the maximum possible volume by transforming a two-dimensional figure into a three-dimensional figure. Prime optimization also has to do with maximizing area. So maximizing area also has to do with maximizing the possible area of a rectangle given the length and the width. Given relationships between the length and the width. Given the perimeter, you have to be able to maximize the area, and then of course with the area, you have to be able to maximize the given volume and the dimensions of the given rectangle. So we will be looking at situations regarding rectangles and boxes overall. So like I said, prime optimization, it has two different forms. So in which you're given the perimeter, and you have to calculate the maximum area. The maximum area potential of a rectangle. We're only focusing on rectangles for now. So of a rectangle. And then you have another situation in which you're given dimensions of a rectangle. To calculate the maximum volume. So those are the two different scenarios we'll be looking at in this lesson. This is a very short lesson, so please make sure to pay attention, and we'll get through this pretty quickly. So let's start off with maximizing area. We're going to look at how we optimize our areas. So when it comes to optimizing the area of a figure, you must be able to undergo two steps in your process. Number one, you're going to develop a quadratic in terms of x that represents your length, width, and area. Number two, you're going to be graphing the quadratic equation and discovering its maximum or highest point, which will actually represent your maximum dimensions to find the maximum area of your given rectangle when you're given your perimeter. So how exactly does this work? So like I said, you're going to get that it's going to have to be in terms of a parabola and a quadratic equation. So I'll show you how to develop that quadratic equation in the next slide. But what we're doing is we're taking the properties, taking relationships, and we're going to develop an equation that shows the correlation between the area and then the dimensions, the length and the width. Afterwards, once we have that equation, we're just going to graph that equation, and then we're going to find the vertex. The vertex is going to be that point where all parabolas meet. You should have learned this in Algebra 1, but we're going to find that maximum point. It should be a downward-facing parabola, and when we find that maximum point, our x value is going to be representative of our length, and our y is going to be our area. So we can merely divide our area by our length to calculate what our width is, and we know all three measurements: our length, our width, and our area. So now let's continue with our optimal area practice, and I'm going to give you a problem. So with developing our equations, I'm going to help you develop your quadratic equations for this given problem, and then of course I'm going to show you the graph afterwards, which is something that you can do on your own with any type of device. I'm not here to show you exactly how to do that yet. Anita does that in her Algebra 2 lessons. I'm merely here to show you how to develop those equations and how to find that given point on a solid graph. So a rectangle has a perimeter that is 580 yards. What is the optimal or maximum area of this rectangle? So we have to calculate that optimal area with the given perimeter. So one thing that we know about area and correlation with a perimeter, we know that our perimeter equals 2w plus 2l. W is going to equal width, and L equals length. So 2w plus 2l equals perimeter. However, we know that W times L, or our width times our length, is going to equal our area. So what we can basically do here is we can divide these values by 2. We can divide these values by 2 to get these values right here, this value right here. So in essence, the perimeter divided by 2 equals the length plus the width. So we're going to divide our perimeter by 2, 580 over 2 equals 260, and we know that the length plus the width is going to equal our 260. So we just need to find those dimensions now. How are we going to develop our equations? Well, we can develop our equations by calculating area. We know that area is length times width. So let's put these values that we know in terms of our length and our width. Let's make our length our x value in our quadratic equation. Quadratics are always in terms of x in this case. So if our length equals x, what we're going to do is we're going to put it in terms of our x value. So we see that y is going to equal our area. So y equals x times our width. So what exactly is our width? We know that if length equals x, we know that the width must equal 260 minus x, because we know that our x plus our L equals 60, our length plus our width equals 60. X and our width, or our length and our width, are going to add up to 260. So we know that 260 minus our given length is going to equal W. So we know that 260 minus x is going to be equal to our width. And then we're going to multiply those across. Oops, sorry, I apologize. It should be 290. My bad. 290 and 290. So you're going to multiply those across. We see that negative x squared plus 290x is our equation, and that's all we have to do from here with our calculations. We're merely just going to plug that into our graphing calculator, and you should get a graph that looks like this with our final vertex at 145, 21,025 yards. So that's going to be a 145 length, and then 21,025 as our area. We can check that by dividing. So we know that 145, we know that 145 and then 290. So we know that it must add together. So we know 145 plus 145 must calculate to that. So this is going to be further prime optimization practice part 1 with our practicing with volume, and then we have another side with another problem. So practicing with volume, essentially what you're doing is you are turning a rectangle into a rectangular prism or box with the optimal value. So you're turning a 2D figure, your area, calculating the area of that given rectangle, and then you're trying to develop the largest possible volume with that given rectangle. So in order to do that, what you're going to have to do is you're going to have to take your rectangle, and in order to fold it up into a box, what you're going to have to do is you're going to have to cut out squares in each and every single one of the corners. Now, that's going to be your x value in your quadratic equation. So let me draw out this rectangle here. So we have this general rectangle here. What we're going to have to do is we're going to have to cut out 4 different squares of equal length on all 4 sides to develop that square and actually develop that box in order to fold these sides inwards. As such, we're going to fold all these sides inwards to form that rectangular prism, something with, depth to it as well, to actually form this right here, our box, as shown. So in order to do that, what we're going to have to do is we're going to have to develop equations in which we make these given lengths of our squares as x, and we're going to try and subtract them from the lengths and the widths to develop our equations. So that's what we're going to do in this slide, prime optimization practice part 2. We're going to solve the following problem and use that same exact concept. So we're going to find the optimal dimensions of a rectangle with a length of 6 feet and a width of 3 feet. So let's start off by drawing out what our rectangle might look like. So let's draw a rectangle here. So with our given rectangle, we're going to have to take out these boxes here. Automatically should come naturally. And then once we do so, we know that it's going to be a 6 by 3. Apologize, let me quickly fix that. Make that a little bit smaller. So those are our 4 boxes that we're cutting out. So it's going to be 3 by 6 feet. Those are the dimensions of our given rectangle, and we're going to be cutting out these boxes here. So what we're going to do is we're going to label these boxes are going to be squares. They're always going to be squares in this aspect. In order to create a rectangle, they have to be. In order to create rectangular prisms, these squares must be these little rectangles must also be squares. So we know that we can label these lengths of these squares as x. That goes with all of these different squares. So they're going to have lengths of x, length and width x. So with their length and width at x, we can calculate what our dimensions are. So we have 6 feet here, correct? So now that we're taking off an x from each side of that 6 feet, this length here is going to actually equal 6 feet minus 2w, because you're multiplying it by 2 w's, but 2 w's is taking off of your width, so now we're going to put that in terms of x. So you're taking off 2 x's from each side. And then for our width is going to equal 3 feet, but we're going to subtract those 2 x's on the width side. So it's going to be 3 feet minus 2x. And then we have our height is automatically going to be our x value as shown here because of this length here. So when you fold it in, that same given height of that square is going to be an x as well. So we know that our dimensions are going to be 6 feet minus 2x, 3 feet minus 2x, and our height is going to be x. We can always multiply that out. So let's multiply that out to get exactly what we want and calculate for the value of x in order to calculate the optimum value of the volume. So we have 6 feet minus 2x, 3 feet minus 2x. We're going to multiply those two together first. So we have 3 times, we have our values here, 4x squared minus 18x plus 18. Then we're going to multiply it by our x value. And we get 4x cubed minus 18x squared plus 18x. And that's how we calculate our optimum volume of this given rectangle. And we know that with this given square here, rectangle here, we only need these two values in order to calculate the optimum volume, because our h is automatically going to equal our x. So once we calculate these two values, we're already gone and set. So this is the focus point. This is all we need to know. All right, everyone. So that'll be it for today's video. I hope you guys enjoyed. This has been the eCoreAcademy learning platform today. Please make sure to like and subscribe down below and turn on post notifications so you don't miss out on any of our channel's latest uploads. And feel free to drop a comment down below. Check out our website at www.ecoreacademy.org if you want to check out all of our extended problems and features that we have there. We have full online worksheets, quizzes, and note sheets that go along with each and every single one of our videos. All you have to do is make an account there for free. You can also email us at eCoreAcademy@gmail.com if you have any questions or if you just want to reach out. Please check out all of our social media accounts down below at Facebook, Twitter, and Instagram to see what kind of interesting content we have there and utilize those mediums to share all of our videos. Once again, everyone, this has been AJ. I really enjoyed making this video, and I will see you guys in the next one. Peace.